Yeah, so with that, we have one set of methods that I mentioned that we'll get to talk about within MCMC. This is, I posted it on Moodle. Hopefully you get a chance to take a look or download if you are taking notes that way. But this is the cases where if you're trying to do Gibbs, but Gibbs doesn't work because you are not able to get the full conditional posterior distribution. So if that happens, there are other algorithms that you can use. So I want to give a high level introduction of those additional methods, because in practice, as we know, you're going to resort to JAGs, because JAGs will do those MCMC estimation for you. But I still want you to know, well, what's JAGs really doing behind the scene. So for that, so I was saying, yeah, not all parameters have recognizable full conditional posterior distributions. So for example, well, if you remember when we have the normal model, when both parameters are unknown, we use conjugate priors in those cases, right? We use normal so we can get a full conditional posterior to be normal for mu, and we use a gamma for phi, right, as the prior, so we get a gamma full conditional posterior as well. But of course, if you start to use some other prior distribution, for example, you do not use normal for mu, but using, for example, I think, yeah, let's just say uniform. Instead of using a gamma for phi, you're using uniform for phi. Then if you try to derive, you can still get a full conditional distribution going on, but you might not be able to recognize what it is. Okay, when that happens, well, like I said, you're going to use JAGs. JAGs are going to do that for you. But if you're curious about what does JAG do when that happens, I just want to show you that JAGs, in addition to doing the regular Gibbs sampler that we talked about, they also utilize widely two other algorithms. The first one is called Metropolis. Okay, the other one is called the Metropolis-Hastings. Both of them are applicable. Of course, they have pros and cons, but both of them applicable when you cannot recognize the full conditional posterior distribution to something that you know that you can sample from, or you can utilize those either of these two to make sure that you can still keep your MCMC going. Okay, so that's the big overview. So let's talk about Metropolis first, and then go to Metropolis-Hastings. So the Metropolis works in this way. So like I said, when this happens, when JAGs, or I should say when Gibbs cannot be done, that is because you cannot recognize what the full conditional posterior distribution is, but you can still get a general form. Okay, you can still derive and get everything over there. So let's talk about the general overview, I guess, the process of doing Metropolis. And here, as you can see, we're trying to estimate a parameter, and let's just say it's a scalar of cos theta given y itself. Okay, so first of all, when you're doing Metropolis, what you do, you of course start with the initial guess, just like the Gibbs. What you do, okay, you have a starting point to get the things going, and you will see that just like Gibbs, Metropolis, and later as well, Metropolis-Hastings, both of them are iterative process. Okay, so you start with the initial guess. Okay, let's just say theta 1. We use that superscript within the parentheses to indicate the index of our iteration over here. So if at a particular S iteration, if I'm trying to get the next iteration for my theta, I should do this. So first of all, I try to draw a plausible value of theta from some symmetric distribution. Okay, we're going to talk about what kind of distributions are there that are symmetric that you can do. For example, as we know, normal is a symmetric distribution. If you try to sample my theta s plus 1 from a normal center at theta s. Okay, so if I have my current draw of theta s, I choose a particular standard deviation, let's just say C, and then, well, if you draw it out, you know that it's going to be centered at theta s. Okay, and then you're trying to randomly draw from this normal distribution. This is a symmetric distribution. Okay, so it falls under the plan of what we mean by symmetric distribution J. So you first of all generate a theta star from this distribution. It could be anywhere, right? As we know when you draw that. And then we're going to evaluate, okay, if theta star is more likely under the posterior that you know, or the full conditional posterior that you already derive, if it's more likely than theta s, then you might want to jump to it because it's giving you a higher posterior or full conditional posterior density. And then if that is the case, I'm going to jump from my theta s to theta star. So I'm going to let my theta s plus 1 to be theta star. Okay. But of course, if theta star is less likely compared to theta s, then you're going to throw like almost like a toss a coin and decide whether you want to stay or not. Okay. So that's the general idea over here. And then in particular, you're going to jump with a probability R defined to be, if you look at the numerator is evaluating the posterior or full conditional posterior of theta at theta star, and the numerator is evaluated at theta s. Okay, so you're essentially evaluating which one is more likely. Okay, and then you're going to determine how to whether you're going to stay or jump, and that's the general idea. Okay, so again, you will still have the expression for this theta given y, you just don't really recognize what it is. Okay, and if you recognize what it is, you're going to go with Gibbs because you can directly sample from it. Okay, but if you don't recognize what it is, what Metropolis is doing is that, let's suppose now you go to another symmetric distribution to make a proposal. Okay, make a proposal of this theta star, and you're going to evaluate which one is more likely, whether it's theta star or theta s, and you're going to decide to stay or jump accordingly. Make sense? Make sense? Yes.
How do you know if theta star is more or less likely on the distribution?
Right. Yeah. So that goes into this equation 2. So the distribution itself can be, well, I guess, calculated or evaluated proportional to, if you look at this, what is it? This will be the likelihood, okay, given that theta star value, and then also its prior itself. Okay, so that's why, yes, when you actually code it yourself, yes, we actually need to rely on what we have learned before about Bayes' rule. So if you're looking at theta star given y, it's going to be proportional to y given theta times the prior of theta star. Okay, and similarly, you do that for theta s as well. Make sense? Okay. Okay. Good. So, and then of course, you're going to repeat this many times, actually a large number of times. And you will also check, you know, when we talk about MCMC diagnostics, it's not only for Gibbs, it's also for, you know, Metropolis that we're talking about. And also next, we're going to talk about Metropolis-Hastings, all of them. And if you remember, when we were plotting those trace plots as well as autocorrelation plots out of the JEX output, well, JEX is doing all kinds of combinations of those different algorithms to make your MCMC work. So the plots that we have seen before is not necessarily Gibbs. Okay, they could be Metropolis and Metropolis-Hastings as well. So that's why you're going to see all of this different shapes of the trace plot. Okay, so let's talk a little bit about that symmetric distribution. It is usually called the proposal distribution. Okay, because you know we're looking at this parameter theta at a particular iteration, and I'm trying to make a new draw out of it to propose as what it's going to be. And it is symmetric in the particular case of what we're doing over there. And let me make sure. Did what I write show up earlier or not at all? Oh, okay. Now it doesn't show up, so I'm not too sure. Okay. Yeah. Anyway, I underline proposal distribution. And okay, maybe once I get to next slide, it's coming back. But nevertheless, okay, so you will see that the way that we write this jumping distribution is theta given theta s. Okay, so that's the current iteration that we're doing. A very important concept over here is that this jumping distribution should only depend on theta s, but not anything before. But if you're doing, you know, like theta given theta s, like what we've shown over here, and like a normal distribution only related to theta s, then that will suffice. Okay, so you should be fine. And for Metropolis, it is a symmetric distribution, meaning that, well, I can get my s plus 1 from my s iteration, and because it's symmetric, I can go back as well because it's, you know, symmetric from each other. And there are other criteria over here. The jumping distribution should be that you can get into any value of the parameter space eventually from any starting value that you have. And also, you don't want to have a distribution that will repeatedly let you go back to the original state because you really want it to be exploring the entire sample space as much as you can. Okay, so that's some features of jumping distributions. But one thing just really keep in mind for Metropolis, it is when we talk about Metropolis, we're talking about this kind of symmetric jumping distribution. Okay. When we get to Metropolis-Hastings, you will see that, well, maybe not necessarily, I really want to go with symmetric distribution. I can get some asymmetric. And if you do asymmetric jumping distribution, it is what we call Metropolis-Hastings. Okay. So it just depends on the particular terminology. Okay. And then, of course, you run your Metropolis and then you do some MCMC diagnostics and you might see some issues, maybe like, some stickiness of the MCMC chain and all that. So one thing that you can really tune is the proposal variance. Let me see if I can. Oh, okay, it starts to work. Yeah, so the proposal variance is how far away your new draw could be from your current draw, right? So if I was doing a normal, as we know, symmetric, okay? So I know if I'm doing a normal, I need to center, right, at my current iteration. And then when I'm making my theta star. So of course I can choose one, for example, with a larger proposal, or I should say larger variance when you have a larger spread. But if I'm doing another possible draw, okay, both of them normal, let's just say. And then, so you can see that, well, if I'm using a larger standard deviation in the normal jumping or the proposal distribution over there, then there's going to have a larger variance, right? It's likely that I'm going to get something farther away from my theta s when I do that. But if I'm using a smaller standard deviation or smaller variance in the proposal distribution, it's more likely that I'm going to get something closer to my theta s. Right? So you can tune that proposal variance itself. And some general guidance over here is that if you have very small variance going on, meaning that you don't move around a lot because you're kind of concentrated around your current draw. So you might have a high acceptance rate, meaning that, well, every time you will jump just because in this particular area, but the moves could be never large enough. And then the chain itself going to be very sticky and highly correlated. Okay. On the other hand, if you try to use larger proposal steps, okay, you will move around the sample space pretty quickly because you will have a big jump, or a big change from your current draw. So it could help you make moves quickly to the posterior mode, but it could also make it really hard to explore the space like widely enough. Okay? So that's why the proposal variance is something that you want to tune after you have done your MCMC diagnostics. Sometimes you might see that it's too sticky and I really want to increase, okay, my proposal step or the proposal variance. But sometimes you see that you get stuck in an area that you don't really fully explore, then you will want to decrease your variance in that case. Okay? So that's some general guideline and all that. And of course, when you code it yourself, you can actually record how many times you're actually gonna accept your proposal, and sometimes you're not gonna accept and stay at where you are. So if you do that, we actually recommend generally to get roughly about 20, or I should say roughly about 35% of the new proposed to be accepted. So that's when you're trying to track how often you accept to the new draws and all that. And of course, this is part of the tune-in. And then if it's far away from this 35 or outside of 20% or 50%, that's where you want to tune that proposal distribution a little bit more. Okay? Yeah, so for example, if you're using the normal jumping distribution that we talked about, you will reset the variance C square, that's the standard, C is the standard deviation. So you can run some short chains and then make sure that, well, maybe for 100 iterations, you get about 35% acceptance with a particular C square. And then if you feel comfortable by then, you can run the chain for a lot longer and then figure out all of your other aspects of the MCMC. All right, so let's look at a Metropolis example. So hopefully it's a little bit more tangible over here. Okay, so this is our normal model, which many of you would recognize that, well, I don't really need to do any kind of MCMC because if sigma is already known or phi is known, I know that if I give a normal prior for mu, I will get a normal posterior. Okay, so this is from the mean chapter that we did before. Okay, so we will know exactly what this distribution is. And if that is the case, you can use you can use Monte Carlo simulation because you already know what it is. You can directly draw from it. Okay. So in that case, how about using the Metropolis algorithm instead? I mean, because yes, I can have an analytical posterior distribution that I can use Monte Carlo already. but we can give it a try to use Metropolis and see how things go. Okay? So let's just propose as a starting point. Remember we talked about jumping distribution of being normal earlier, so you can have a symmetric jumping distribution. But another very commonly used jumping distribution for Metropolis is uniform. Okay, so if I center at my current draw, and I just give, minus C, and then plus C as a range, as my normal draw, that will be another symmetric distribution, right? That will be a symmetric proposal distribution. So in that case, that's what equation 7 is about. So here you see, we're going to propose to draw a mu star given my mu s. So this uniform is centered at mu s, okay? But then with length C on the left and with length C on the right. Okay, so I can do a uniform within this interval, and this is a symmetric jumping distribution. So this falls under the Metropolis algorithm as what we talked about. Okay. So step 1 is you're gonna draw a new value. You can use R uniform in R in order to get a new value of mu star. And then you're gonna calculate the ratio. So this is related to what Carl was asking earlier. You can actually calculate all of this accordingly. So we have the prior over here, okay, and we also have the likelihood that you need to do. So remember Y itself, the data model, it's a normal model itself, okay, so that's how you will be able to calculate this part itself. So let me show you examples, so then later I can ask you in another context. Okay, so here, if you look at what we have over here, okay, if I'm trying to, so let me try to illustrate. In order to calculate this part, okay, so this requires what? I already have a mu star value, right? Like I already take a draw. I don't know what the value is, but I have a draw. So when that happens, I have a bunch of data. And remember, this is still a normal model. So the sampling itself is a normal. So you can use d norm of each observation evaluated at this mu star value. And then whatever the sigma is given to you, make sure that you product all of them in order to get the likelihood. So that's in practice in R, that's what you're going to do. Similarly, for the denominator, when you're looking at the likelihood, you will also use the d norm, evaluate each of the yi, and you're specifically evaluating at this mu star, mu s value, because you're evaluating this py mu star. So this is, so the first part in the box correspond to how you evaluate this part. Okay. The second part, as we know, is the prior part. And if you remember, the prior we give is the normal itself. Okay, we're still talking about the normal. The uniform is the jumping distribution. Okay, however, the prior themselves is still the normal itself. So you can use d norm and then evaluate both mu star in the numerator and then mu s in the denominator at the prior parameters that you have over here. Okay, so this is in practice. How you can evaluate or compute this R, and then you'll be able to determine whether you're going to jump or not. Okay? Okay. Yeah, like I said, in practice, or at least in this course, I don't think we'll code it ourselves, because we're always going to go back to JAX and let JAX do all of this, but this is behind the scene what JAX does. Okay? So one caveat, if you ever do this by yourself, is if you look at equation 9, this is a bunch of density being multiplying together. It could be really small. So for computational stability, people usually, instead of doing that equation itself, they would do everything on the log scale just to make the computation a little bit more stable. Okay, so just so you know, and this you might have encountered in other contexts as well. But whenever you have, especially producting a bunch of, density function, if they're really small, you're going to have very small value being producting together. If you have 1,000 or 10,000 observations altogether, this will be something very small. So instead of working on the original scale, you can work on the log scale. And then when that happens, well, everything is about on the log, but at the very least, the computation will be much more stabilized. So in case you ever try this, but like I said, we're going to use JAX for most of the time, but this is what JAX doing. So I did include a, it's not runnable, I didn't make it run, but nevertheless, you should be able to get a sense of how you can do this by yourself if you ever want to code it up. So you can see that we first of all get a uniform draw, right, from this uniform jumping distribution, my R unit, and get my proposal from you. And then I evaluate the likelihood function and all that. I calculate my log of R, and then I'm going to determine whether I'm going to jump or not. So this is the general step of how you can do this Metropolis. In the code, in the class notes, I also include another example, which is actually an independent study a while ago that was extending their Bayesian statistics project. So they were looking at a different Q Gaussian model, and then they need to code it up for the entire Gibbs, entire MCMC that using Metropolis. So this is another example if you ever want to look at it a little more carefully. Okay. So that's the Metropolis. Metropolis-Hastings is another type, but you can see that they're highly related to each other. So Metropolis, we use jumping distribution that is symmetric, but then for Metropolis-Hastings, we might want to use something not symmetric, and that's when you want to do a Metropolis-Hastings. Okay. So the motivation of that is sometimes if you draw draws from symmetric proposal distribution might not be very efficient. It might take a long time to converge. So in that case, we might want to do something asymmetric, and that's where we're gonna do this Metropolis-Hastings. Okay, so for example, in some cases, maybe instead of using a normal, okay, you might want to use a asymmetric distribution like gamma, because it might be a better or closer approximation to it. So when we do that, well, instead of doing normal, we do a gamma. For the proposal, as well as determining whether we're going to jump or not, we need to actually add a correction for the acceptance ratio. So we will be able to make sure that we have done this correctly. Okay, so that's the motivation itself. With that, you will see that it's very similar in some sense, just some kind of corrections here and there when we're trying to, instead of doing Metropolis, to this Metropolis-Hastings. So you're still going to have a proposal distribution, like I said, okay? And you take a new draw, okay, from this proposal distribution. And then we're going to compute the Metropolis-Hastings ratio, okay, something very similar to what we did before. And then also, but we do a little bit correction using the minimum over here. And then we will be able to decide how we're going to jump using probability calculation as well. Okay, so this is the big picture. We also have examples later on as well. So earlier in the Metropolis, this is the ratio, okay, that we decide, okay. Right now we're adding this correction coming from the proposal distribution evaluation as well. So we're able to make sure that things are right. And just so you know, also back then, when we're working with the Metropolis, because the jumping distribution is symmetric, so they cancel out. That's why you didn't have that in the Metropolis case. But then in the Metropolis-Hastings, we're using that as a correction. So we're going to keep that over here as before. All right. So again, some features over here, just like before, the jumping distribution, whenever you're doing it, should only be depending on theta s, but not any previous draws. Okay. Just like before, you want a jumping distribution that can get you anywhere from anywhere that you start, and do not return you periodically to the previous steps, because otherwise you would really not get out of it. Roughly, again, 35% is the rule of thumb of the acceptance rate when you're doing this over here. And make sure that you use appropriate jumping distributions in the particular context. All right. So with that, I want to show you the normal example once again. Okay, so we still have the known sigma over here. So in that case, we know the analytical posterior distributions and then normal. So instead of doing Monte Carlo directly, let's try to use Metropolis-Hastings. So we saw that example earlier for Metropolis, and we use a uniform, right, as the symmetric jumping distribution for normal. So right now, let's see. Okay, maybe instead of doing asymmetric, let's do a gamma asymmetric. Okay, and I'm determining the gamma using the first draw, or I should say first parameter centered, or I should say add my particular current draw, and then I'm determining how I'm going to jump over here. So step one is I'm going to draw a mu star from this gamma. Okay, and the next step is I'm going to calculate the ratio, and just like before, the ratio depending on how we're going to do this given the data itself. So if you look at this, this is going to be a normal, right? Because this is the data model. This is also a normal. because this is from the prior as a normal, and this is the gamma. Okay, so you see that when you're looking at the three different, so very similar to the previous one that we have seen, but instead of only the first two, we have the last correction factor as well, and we know that it's coming from equation 19. So in that case, I'm gonna have a d norm for my likelihood. I'm gonna have a d norm for my prior. I'm gonna have a d gamma given my proposal distribution. So that's what you will do when you code it up. Okay, so like I said, and just like what we talked about before, when you're taking product of those very tiny values, quantities in a large number of times, then you will want to work everything on the log scale just to make it stabilized. All right, so that's the example of what we can do instead of equation 22, that on the original scale for this alpha star, you're going to do this on the log scale, so you'll be able to work with the calculation. So the code works in this way. As you can see, the log of the R itself going to be slightly different because we're going to have the norm. That's fine. And then we also have the normal and everything over there. So make sure that, well, if you ever want to give it a try, take a look of what you can do. And I should say that this is from the original Metropolis. So we need to add something, right, to this in order to add that gamma. And this is how you can play it out later if you ever get interested in exploring this a little bit more. Okay, so like I said, for us, really, we will use JAGs for all of the non-Gibbs case. And even for Gibbs, we're using JAGs. But I think it's important for us to know what JAGs is really doing, because Gibbs is not the solution for every problem that you're going to encounter. Like I said, if you won't be able to recognize the full conditional posterior distribution, then you will never be able to use Gibbs. Okay? But if you are able to do this using other algorithms, that if you don't recognize what the full conditional distributions are, you can use Metropolis or Metropolis-Hastings. And of course, since we don't talk a lot about this in class, if you actually want to dig this into a little bit more as part of your project, that is totally fine as well. Okay. So that's just another option, I guess. This will fall into option, I guess, number 2 or 3 for the project options. That is like exploring some of the methodology a little bit more, and then you can do some simulation studies or applications as well. So yeah, just to wrap up, I think as you can see that if you only have a single parameter in your model, things are pretty easy to work with. But as soon as we have complicated models, we have what we call multi-parameter models. And then because of that, you're going to have multi-parameter Markov chain Monte Carlo as well. So the computation can always be a little bit more challenging. But for JAGs, for example, they are using a combination of Gibbs, Metropolis, and Metropolis-Hastings. They just really depends on in the model that you're fitting and also the data set that you're using, which one is the best to do. So they're actually optimizing it for you behind the scene. So I think with that, I will wrap up, I guess, with this extra material. And like I said, if any of you find this very interesting, like the computation side of things very interesting, this will be a good project topic if you want to dig this into a little bit more. And I can definitely direct you to certain resources if you want to give a little bit more reading about this. So with that, I would just say, I think I would just give back the midterm exam, and then we're gonna end for today, also before the break as well. So if you remember, we have, I'm just going to use this slide, so just talk about it really quickly. I think we have a 30 points for the, what is it, for the written, and then the 20 is for the take home. So the take home I already posted on Moodle with your graded solutions and all that, so you should be able to see grades and everything. And as far as I can remember, I think the mean for the, let me think. Yeah, so I think for the mean for the take home is about 18. So everybody did pretty well. I think the mean for the written exam, which I'm giving back right now, is about 25. So just give you a sense of how the whole class is doing. And I will mention this in my email later to class as well. So you will see that we'll get the chance to do midterm exam corrections. Okay, once you get the chance to look at your exams and then redo some of the problems. The plan is you will make an appointment with me if you want to do corrections, and then if you can do it correctly, like all of them correctly or any of the points correctly, you will get 25% of the missed points back. Okay, so that's the plan for both the return and the take home. So you can do that for both. So on Moodle, I think I already posted the grades for both the return and the take home as well, but I have the take home is already posted directly on Moodle, so you can look at your graded results. But for the take home, sorry, for the written exam, this is what I have. So let me make sure that I don't record this part, it's too much. And then I will